All right, welcome back. So in this video, we'll be looking at the background and I'm going to go over the terminology of figuring out what a solution and what a solution is for a differential equation. And then we'll look at the formulation of what's called an initial value problem. So let's get started. So to go over some terminology uh, in the when it was referred to in the previous video, an ordinary differential equation is an equation with only one independent variable, right? So with one independent variable. So, for example, uh, like the like this differential equation, right? This here is an ordinary differential equation because the independent variable is x, right? So, and actually mentioned this at the third bullet point. So, if the equation involves a derivative of one function, right? Usually it's x, it could be y or some other letter, right? With respect to another variable, let's say t, the former is called the dependent because x would be dependent on t, and then the latter is the independent variable, right? So as an example, oops, um, darn it. So yeah, so as as an example, the uh, this right here, this right here. Let me write this out as d squared x dt squared plus a times dy dt x. Right. So t is the independent variable. And then x is the dependent. Right? Dependent variable. Okay. And also there's another set of there's another term I have to go over. It's what's called the order of a differential equation. So the order is the order the highest derivative present. So in this case, we have a second derivative occurring in this equation. So we say that it's in order 2. Okay. So in other words, they call this type of equation, so they call this type of equation a second order differential equation. Okay. Second order ordinary differential equation. All right. And then lastly, there's actually what's called a linear differential equation. And a linear differential equation looks like this, right? It looks like this form, right? Um, these coefficients here, oops, are actually okay. So these terms right here, these coefficients, they are coefficients in x, right? These are functions of x, right? And then capital F of x is just another ordinary function in x. If the capital F of x is 0, then the ODE is called homogeneous. It's what's called a homogeneous differential equation. Okay. So, yeah, homogeneous. I'm pretty sure I spelled that wrong. Homogeneous. Homogeneous. Okay. So, as an example, as these couple of examples right here, uh, these are linear differential equations, right? Because, right, the coefficients, uh, the coefficients are that are multiplied by the derivatives in y, right? They are functions in x, right? They are functions in x. So clearly the first one, clearly part A is a linear differential equation, right? So it's a linear first order, right? Because the highest derivative in part A is only one derivative, right? Y prime of x. Um, okay, this this example should be y double prime of t, my triple prime of t minus cosine of x times y double prime plus 5 equals to e to the t. It's supposed to be that function. Um, yeah, so in this example here, this would be a linear third order, right? So this is a third order. Linear ODE. This will be much more difficult to solve, but um, yeah, so at this point, yeah, yeah, we don't have to worry about this type of equation occurring for now. Um, yeah, we'll use a different method to solving this type of differential equation, right? But in this example, we're just looking at the classification, right, of what the differential equation is. So in this case, this is a third order linear ordinary differential equation. Okay. So, uh, yeah, so here's some examples of differential equations that are non-linear. Okay. So part A, this says dy dx plus y cubed is 0. Now notice the y is cubed, so this is non-linear because of this term, right? The y is cubed. So it's non-linear because of the y cubed term. Remember, the function y and the respective derivatives cannot have powers, right? It cannot have powers. Likewise, for part B, we have also another example of a nonlinear differential equation. So this should read as so y double prime of x plus y times y prime of x is 0. Okay. This is also nonlinear because of this term right here, y times y prime of x. Okay. So, oh, Jesus. Okay. So let me write out the full details of part B in of this example right here. So we have y double prime plus y times y prime of x equals 0. This is nonlinear. What order is it? It's a second order. Okay. Ordinary differential equation. And it's nonlinear because of the y times y prime of x term. That's what makes it nonlinear. Okay. All right. So, yeah. So that's how you classify various types of differential equations. Okay. So let's go over some definitions here. Okay. So in order to show a function as a what's called an explicit solution, right? So a function, what's called phi of x, when substituted for y in either in this equation, so you're going to have two formulations of a differential equation. So you will have either in this form, y prime, y double prime, y triple prime. So this is what's called the implicit form. And then the explicit, so the implicit form, let me actually write it down here. Yeah, so let me write out the implicit form down here. So a function b of x or g of, actually I'll start off with this one. So if you have a relation capital G of x, y being equal to 0 as an implicit solution, it has to satisfy this equation, right? Which you label capital F as a function with respect to the independent variable x. This is the independent variable. And then y prime, y double prime, y triple prime, and the nth derivative of y are dependent on x. Okay, so capital F is just the implicit expression of a combination of x and then the y function and its derivatives, right? As opposed to an explicit solution, it will look like a variation of this form, right? So if you can solve the nth derivative in terms of a function, it's y triple prime. So this is an explicit form as opposed to this equation on the bottom. This is implicit. Okay. So explicit, you can solve the nth derivative of y in terms of x and all the derivatives up to n minus 1, right? So if you have an explicit solution, let's say phi of x, if you substitute that solution into this equation 1 or 2 here, on the interval I, so I is defined for all of where all x values are defined, right? B is what's called an explicit solution, right? And if you have a implicit expression, so you have x y equal to 0. If it's an implicit solution, it has to satisfy um, um, it has to satisfy this equation here, right? So the implicit equation. So let's go over some examples on how we would show this. Okay. So here's an example. Show that x times y cubed minus xy cubed sine of x equals to 1. So this is an implicit equation. So we want to show that this is an implicit solution to dy dx equals to x times cosine x of sine x minus 1 times y divided by 3 minus x minus x times sine of x on the interval 0 pi over 2, right? And if you solve the denominator equal to 0, right, you get clearly those values, right? So x minus x sine x is 0, which means that x is 0, or 1 minus sine x is 0, okay? Sine of x is periodic, so we only want to figure out the function where it's where the general solution is well defined. So they just let x equal to pi over 2, right? So um, that's where you have a well defined function, right? So anyway, to show the implicit equation is a solution, right? So let's start off with this. It was xy cubed sine x equals to 1. Well, you have to recall related rates in calculus. No, related rates. I meant implicit differentiation, right? So we're going to use implicit differentiation. Because remember, right, y is a function of x, right? When we're differentiating y with respect to x, we're saying that y is a function of x. So y is now a function in x. So if we differentiate both sides with respect to x, right? So we'll have d dx of xy cubed minus xy cubed times sine x equals to, well, the derivative of 1 is 0, right? So it's 0, okay? And so we'll have d dx x times y cubed minus the derivative with respect to x of xy cubed sine x is 0, okay? So this first term, right? So this first term will be a, so we're going to use the product rule. Okay. I'm trying to work this. Okay. So the first one, yeah, so we're going to use the product rule here. Let me erase this up. Okay. So we're going to use implicit differentiation. Okay. So by the product rule, let me zoom in here. We'll have that this quantity will equal to, so by the product rule, we'll have y cubed plus x times 3y squared, but y is a function of x. So we have to use the chain rule. So we have to tack on a dy dx term, right? For the other term, this term right here, that will be minus, I don't like that color. Let's just do this. I'll do orange. So for the orange term, it will be minus. We have to use the product rule again. So we'll have x times sine x times 3y squared dy dx. Okay. And we'll have a plus, so we'll have a plus y cubed times the derivative times the derivative of x times sine x. So we have to use the product rule there as well. And what we have now is, so, okay, if I go here, all right, so this is equal to y cubed plus 3x y squared dy dx minus yeah, okay, so I'll have, all right, I gotta be careful here, so darn it. Okay, I gotta be careful. So I'll have 3xy squared sine x dy dx, and then and I'll have a minus y cubed times, I'll have a sine x and then plus x times cosine x. Okay, that's plus cosine x. All right, so I zoom out here. So this, this should equal to, so I'll have a y cubed plus 3 x y squared. And then I'll have, oh, oops. And this should equal to 0, by the way. So at that entire left-hand side. So, okay. No, actually, let me do this. Okay, so y cubed, and then I'll have a minus y cubed times sine x plus x cosine x. This would equal to 3x y squared sine x, and then plus minus minus 3xy squared dy dx. Okay. So uh that is if you want to combine like terms, right? So we have this dy dx term over here and this dy dx term over here. And since this whole expression equals to 0, we can just gather all the dy dx terms on one side of the equation, and then all the other terms on the left hand side. So okay, so we'll have so what this means is we'll have a y cubed times 1 minus sine x plus, oh shoot. Hold on a second, I gotta be careful. So, Jesus Christ. All right, so yes, so be 1 minus sine x plus x cosine x divided by, so I will get um 3xy squared. 3xy squared sine x minus 1 equals 2 dy dx. If we solve for dy dx, right? So we'll have y over 3 times x. In the numerator, I'll have 1 minus sine x plus x cosine x over 3x times sine x minus 1. And if we factor out a negative sign in the numerator, we'll get the exact solution that we want. We'll get the exact solution that we want. So if I erase this here, so if I factor out a minus sign, right, I'll get, so if I factor out a minus sign, I will get, yeah, okay. Right. Yeah, so, or I'll factor out a minus sign in the numerator. Yeah, okay, so, okay. Yeah, so if you factor out the minus sign in the denominator, right, so this is minus 3x, and then 1 minus sine x, and then just multiply the negative sign by in the numerator, you'll get the solution that we want. Okay, so that's one way of approaching it. All right. So, yeah, so that's one way to arrive at a solution. So what I want to look at now is so this once again, this is the general form of an implicit nth order differential equation, right? I mean, any differential equation can be solved implicitly like this, okay? But not many equations can be formulated explicitly, okay? Any differential equation, any ordinary differential equation can be looked at implicitly, right? So another way is, yeah, just show that your function g of xy equals to 0 is a solution to, I'll just call it capital F, right? F equals to 0, right? And then what I'm going to go over next is what is called an initial value problem. Okay, so by an initial value problem for an nth order differential equation uh, that is implicitly defined like this, okay? What we mean is we want to find a solution to the differential equation on any open interval I that contains a point x naught that satisfies the initial conditions, the n initial conditions, right? These are what are called initial conditions, okay? X naught is an open interval I, and then y0, y1, and y sub n minus 1 are constants, all right? So our goal here is figuring out a what is called a particular solution to the ODE. Okay, ODE. So let's look at one more example or some more examples. So like this one, here's another example. Determine whether the given function is a solution to the differential equation. So we have this function, right? Sine of x plus x squared. And we have to show that y is a solution to this differential equation, right? Second partial of y with respect to x plus y equals to x squared plus 2. Okay, well, one way is just look at what y is equal to, okay? And then from this equation, we have to take the second derivative of y. Then we have to add its original function, and we have to make sure it equals to x squared plus 2. That's our goal. So dy dx, or y prime, and this is another point I want to mention. So there's different notations on derivatives that you'll see. Let me zoom out here just real quick. Okay, so sometimes you'll see like derivatives as like y prime or dy dt, right? this is the notation of the derivatives, but they mean the same thing. So what dy dt is the first derivative of y, right? Sometimes you'll see y dot in some textbooks. So y dot, it just means the first derivative, right? So you could see like y double dot, which means the second derivative, right? Y double prime like this, the Leibniz notation, okay? So that's important about the notation of the derivative. So anyway, so what we need to do is figure out how to show that this is a solution to the differential equation. So now y prime, well, that equals to cosine x plus 2x, right? And then y double prime would be negative sine of x plus 2, okay? So what this means now is, so here's our equation. So y double prime, okay, with respect to x plus y, it has to equal to x squared plus 2, right? So y double prime of x was this quantity here. So we'll have a negative sine of x plus 2 plus y of x, which is our given function here. So plus sine of x plus x squared, right? What's cool about this is that the negative sine of x terms will cancel, and then we'll have our result, x squared plus 2. Okay? So, yes, it's a solution to the differential equation. All right? So, hopefully that made sense. Let's look at an initial value problem. So, what I want you to do is I want you to try and verify that this function, phi of x right here, try to show that this is a solution to this linear equation. It's a second order. So it's a second order linear differential equation, okay, with constant coefficients. We will learn in future videos on how to solve a second order differential equation of this type. And it's relatively easy, okay? So this is a second order linear differential equation, okay? And you have to show that this function works for any constants C1 and then C2, okay? And then the other part is we want to determine exact numbers for C1 and C2 such that y of 0 equals to 2 and y prime of 0 equals to 1. So pause the video and I want you to work on this example real quick. And I'll show you the solution later. So good luck. All right, so I assume that you had this example completed, so let's actually go over it. So you want to show that phi of x is a solution to equation, I'll write out star, right? So we know that phi of x, this is c1 times e to the x plus c2 e to the minus 2x, okay? So that means phi prime of x, well, that equals to c1 times e to the x minus 2 times c2 e to the minus 2x, okay? We also need the second derivative, right? It's a second order differential equation. So the second derivative would be c1 times e to the x plus 4 times c2. e to the minus 2x. Okay. So what that means is, so this equation will become, so this equation will become, so phi double prime of x plus phi prime of x minus 2 times phi. This has to equal 0. So what that means is we'll have c1 times e to the x plus 4 times c2 e to the minus 2x plus phi prime of x, which is c1 e to the x minus 2c2 e to the minus 2x minus 2 times phi of x, c1 times e to the x plus c2 times e to the negative 2x, okay? And you know what? I am going to write this out a little bit bigger so we can see the whole picture here. So, oops. So we have c1 e to the x plus 4c2 plus c1 e to the x minus 2c2 e to the minus 2x minus 2 times c1 e to the x plus c2 e to the minus 2x. And this has to equal 0, right? So we have a c1 e to the x, right? c1 e to the x plus another c1 e to the x. But we have a minus 2c1 e to the x here. So this would be 0, right? Likewise, we have a 4c2 e to the minus 2x. Okay, minus 2c2 e to the negative 2x. So that would be a 2c2 e to the negative 2x. And we have a minus 2 times c2 e to the minus 2x. So this here would be 0. So in the end, it equals to 0. Great. So that is done. And what we also need to do is figure out what's called a particular solution, right? A particular solution for this type. All right. So we know that one solution, y of x, well, it equals to c1 times e to the x plus c2 e to the negative 2x, right? Now, there's two initial conditions, right? Since we're dealing with a second order, right? Since we're dealing with a second order differential equation, there's two initial conditions. It has to be. Y of 0 equals to 2. What that means is when x is 0, the y value is 2. So all you have to do is just plug in 0 in for x in your solution. And this has to equal to 2. So what this means is that C1 plus C2 equals to 2. And we also know that y prime at 0, y prime of 0 equals to 1. So here was phi prime of x over here. So that would be the same as y prime of x. So what that means is we'll have C1 minus 2C2, and that has to equal to 1. Okay? So what it turns out is we have a system of linear equations here, right? C1 plus C2 is 2, and then C1 minus 2C2 equals to 1. You could solve for C1 and C2 by elimination or substitution, but I'm going to use elimination. Right? If we subtract the equations together, the C1s will cancel, and then we'll have 3 times. What the heck just happened? All right. Hold on. Can I erase this, please? So let me erase this again. There we go. So we'll have 3 times C2 equals to 3. I'm sorry, 1. 2 minus 1 is 1. Okay, so 1. And so C2 is 1/3. And if C2 is 1/3, C1 is equal to 2 minus 1/3, which is 5/3. Okay. All right. So our particular solution would be, so C1 is 5/3. 5/3 e to the x. Excuse me. And then plus 1/3 e to the negative 2x. Okay, e to the negative 2x. All right, so that's an example. Those are examples on the background of differential equations. Classifying which differential equations they are, and figuring out solutions and solving initial value problems. Okay, so here's some problems for you to check comprehension. All right, they're in the textbook. So these should be relatively simple to complete. So this here is 1 through 12, right? So if you have questions, just please let me know in the comments. And then next time, what I'm going to talk about is looking at direction fields, right? Because because all what a derivative is, it's looking at the rate of change, right? And it also defines a slope of a tangent line. So we can classify what a solution curve looks like just by drawing in tangent lines, essentially. Tangent line segments, okay? That's what direction field is. But more on that later. But for now, thank you for watching. I'll see you next time.